Hi, I'm Will Thomason, a PhD candidate at Cornell University, where I work on planning algorithms for robotics. Planning algorithms in the real world need to be robust, meaning that they can complete tasks despite perturbations and incomplete information, because the real world is hard to control and hard to precisely model. They also need to be efficient, meaning they can solve problems quickly, because many real-world problems don't give much time for deliberation before needing action. Finally, we want these algorithms to be flexible, which means they're both accessible to non-expert users and easy to adapt to different problems and environments. Many planning approaches in robotics provide one or more of these properties, but few, if any, provide all of them simultaneously and to a sufficient degree. As a first step toward this research vision, I've created Planet, which is a sampling algorithm that can be used to turn any sampling-based motion planner into an integrated task and motion planner. Integrated task and motion planning is an area of robotics that studies solutions to problems with logical and geometric constraints. Planet works by introducing a continuous interpretation for discrete symbols that lets it directly sample states relevant for a given task and bias a motion planner toward these states. Planet produces reasonable plans as output and is competitive in performance with other state-of-the-art task and motion planners. Further, because it's just a sampling algorithm, it's easy to use with a wide variety of motion planners and robot platforms, contributing toward my goal of flexible robot planning. However, Planet is not especially robust. It assumes deterministic action execution and produces open-loop trajectories. It also does require some expert knowledge to set up and use. My current and future research works to mitigate these shortcomings. One particular project is something I call automatic abstraction refinement. In task and motion planning, we typically abstract actions as maps from sets of states that satisfy constraints necessary to run the action to sets of states that have had the action's effect applied. However, constructing this map correctly has important implications for planner performance and is difficult to do. Automatic abstraction refinement tries to start from an easy to create and even potentially incorrect abstraction for an action, and by observing how that action works in the real world, automatically create a refined and corrected version of the abstraction that can be used to make a planner faster and more robust. I'm also working on a reactive, robust approach to task and motion planning based on ideas from model predictive control. This approach starts by constructing conservative estimates of constraints on the space of solutions to a problem, and then making partial plans that satisfy these constraints, and choosing the best of these candidates to start executing. By observing this execution, the planner can automatically refine and repair its action abstraction, update its estimate of the constraints on the solution space, and continue iterating until the goal. This allows a robot to start acting faster than a fully deliberative planner, and also react to unexpected events during execution. Taken together, these techniques can provide a fully robust, efficient, and flexible robot planner.